Okay, then I thank you all for joining and give the stage to you, Julian. Thank you for being here.
Thank you very much. This is me, Julian Samaroo. Thank you for the introduction. I greatly appreciate it, and I'm super happy to be here today. Two screens. You'll see my script to the right, which is fine. You can read ahead if you want to. And you should see Hello World to the left.
Yes, I see the full screen.
Awesome. Okay, well, let's get started. So let's just load Dagger data frames, which is what we're going to be starting out with, although these are already loaded. So let's start with briefly discussing what is Dagger. So parallelizing codes with distributed.jl, which I imagine we're all kind of familiar with, is pretty simple and can provide an appreciable speed up. But for complicated problems or when scaling your problem to larger sizes, the APIs are somewhat lacking. Dagger.jl takes parallelism to the next level with support for GPU execution, fault tolerance, and more. Dagger's scheduler exploits every bit of parallelism it can find and uses all the resources you can give it. The distributed standard library exposes RPC primitives, remote call and remote channels, futures, and so on for coordinating and executing code on a cluster of Julia processes. When a problem is simple enough, such as a trivial map operation, the provided APIs are enough to get great performance and pretty good scaling. PMAP, at distributed, etc. I imagine most of you are familiar with those.
Julian, a little request. Could you increase the font size of your terminal?
Yes, absolutely. Let me see if I can figure out how to do this.
And I think there are also a couple of completely new ones to Julia. So PMAP, that's the standard parallelization routine available in Julia built in. And with this, you can just execute the same function on multiple machines doing the same thing. So that's the very basic thing, and that's called map from functional context, and PMAP for parallel map then. So parallel mapping.
Here we go, bigger. Let us do this. Okay, is that all right, or do you want the left terminal a little bigger?
A little bigger still.
A little bigger? Okay.
Appreciate it. Yeah.
Just shrink the bottom a little, if I can. If you're wondering, macOS is not what I daily drive. I actually run Alpine Linux normally. So this is why I'm a little bit confused with this. How's that? Is that better? Good size?
It's better. A couple of command and plus would be very appreciated.
There we go. Much better. Okay.
Yeah, I think now we are going smooth.
Cool. Okay, let's go with this. So this isn't too huge because there is going to be some output. So we don't want to fill up the screen too much. So where was I? Okay. So distributed has APIs, great performance, pretty good scaling. However, things will change when one wants to use distributed for something complicated like a large data pipeline with many inputs and outputs, or a full desktop application, or when using an HPC system with code that is not simply embarrassingly parallel. While you could build these programs with distributed, you would quickly realize that a lot of functionality will need to be built from scratch. Applications scale fault tolerance and checkpointing, heterogeneous resource utilization control, and even simple load balancing. This is not distributed's fault. It wasn't designed to have all these features. Some may say that it was designed to be the be-all, end-all for distributed computing, but it's really not. It just provides some simple tools that you build on top of. So Dagger.jl takes a different approach. It's batteries included distributed computing, and it has a variety of useful tools built in that makes it easy to build complicated applications or simple applications that can scale to whatever kind and size of resources you have at your disposal. Dagger ships with a built-in heterogeneous scheduler, which can dispatch units of work to CPUs, GPUs, and future accelerators to be decided. Dagger has a framework for checkpointing and restoring intermediate results, and together with built-in fault tolerance, allows computations to safely fail partway through and be automatically or manually resumed later. Dagger also has primitive to build complicated dynamic execution graphs across a cluster, so users can easily implement layers on top of Dagger that provide abstractions better matching the problem at hand. So we actually have this little section above here. This is not what we are going to do. We are not going to get ahead of ourselves and show off very fancy features because frankly, most people are not going to use those. Let's start at the roots. How do we use Dagger? How does it work? And how can we best utilize it for solving our own problems that we deal with day to day? Let's start off with one of the first APIs that many users will use, which is the table API. So let's go ahead and create a data frame. And we are going to have two columns, A and B, where A is sampled from the integers between 1 and 4, and B is just the characters from A to D. And, well, so everyone's kind of familiar with instantiating a data frame like this. Now, let's create what's called a D table. So a D table is Dagger's distributed table. It's reasonably new. But it's rapidly gained features and performance capacity. And it essentially wraps other tables in the Julia ecosystem. It's not specific to data frames. You could use type tables, index tables, a vector of name tuples, anything that is tables.jl compatible will work. Now you see that I provide two arguments to dtable. I provide the input data frame, which we're going to wrap, and then the second argument. So the second argument is the chunk size. So what the dtable does under the hood is it takes an original table and it splits it into partitions. Here we see that we have 10 partitions. And under the hood, they're just individual data frames. There's nothing special about them. However, Dagger can use this partitioning to optimize operations that you do on the dtable. So let's just confirm that. So if we take a look at the chunks field and we just take a look at the first chunk or partition in there, we see we have an 100-row data frame. Our original data frame was 1,000 rows, so split into 10, of course, you get 100 rows. So now if you actually want to convert a dtable back into a data frame or whatever the underlying data type is, you use the fetch function. We'll see a lot of fetch in this tutorial. Dagger and its APIs, such as the dtable, are asynchronous. We're fully focused on asynchronous programming, so if you do an operation, it's not necessarily completed by the time the function call returns. It's running in the background. So if you use fetch, you can actually get a representation of the result, which will effectively wait on the operation in order to get that result. So here, we're just seeing the original data frame, essentially, in all 1,000 rows. Now, if you want to see the underlying table type, you can, of course, just enter it at the REPL, or you can call table type on the dtable, and in this case, it's a data frame. So great. So let's start with some simple operations. So now I'm going to copy and paste just so you don't hear my loud typing, and so this goes a little faster. So let's do a map operation. Let's convert the integer argument for the A column into a string, and let's concatenate that with the character in the B column. Now, this is going to take a little bit. I have not yet had the chance to warm up the terminal, but it's going reasonably fast, which is great. So here we see we've concatenated 1A from the original, 4D, 1D, etc., as you'd expect. So the dtable also has a reduction API. The reduction API is a little simple right now. The function that you specify here, multiplies, is applied to all columns. And so sometimes that's what you want, sometimes that's not what you want. In this case, it kind of works. It works fine for the B column. For the A column, we end up having an overflow, or at least that's my understanding. And we end up with a 0, and then 0 times everything is 0. So that's not terribly surprising. If instead we wanted to just work with the A column and say we just wanted to summate it, then we can do that by using a map to pull out the A column into its own D table, and then do a reduction on that. And here we get the answer you might expect. We also have the filter operation. Obviously, that's needed all of the time. And here we can filter the B column on the value D, on the character D. And that returns all of the rows that match that constraint. So Dagger's D table also recently gained a group by operator. I'm sure if you've worked with tables, this is very familiar. Here we're going to group the D table on the B column. And what this will do, it will construct a special type of D table called a GD table. You don't really have to worry about that too much. And that's split into its own set of partitions. Now this has 4 partitions with 4 keys. For example, those keys are actually, you can see them in the index. We have A, D, C, B. Those are the unique set of values that were in the B column. So now this GDT, this grouped D table, is partitioned according to B. So if we want to, we can conveniently check, we can look at a single partition. So say the partition or the grouping where the B column has the value C. So if we just say GDT of character C, we'll get a lazy representation of that. Nothing's been computed, nothing's been pulled out. In typical fashion, to actually get that value, you use fetch. And as we can see, these are all the rows that have C in the B column. So if you're also working with, if you're doing this in the REPL and you're working with a table that doesn't have a whole lot of unique values in the column you're grouping by, you can actually iterate over all of those groupings. This makes it easy to kind of do exploratory data analysis. So here we can see that we get a key, and then if we just look at the first row of that table that's returned, we can see they match A, D and D, C and C, etc. So pretty straightforward. So now let's move on. Let's show off a little bit more of the tables.jl integration, because that's important. That's, you don't want a table type that doesn't integrate with other table types. That can really make your life difficult if you don't have that. So let's work with CSVs a little bit. So let's go ahead and let's take just our original input data frame, no D table, and let's write that out to a CSV. Now this will, of course, take a second because, well, apparently it won't take a second. That's great. Okay, so now we have a test.csv, and that has all of our data. Now we can, of course, this is all just regular data frame stuff. This isn't, terribly surprising to most people who have done work with tables. But you can do a csv.file and pipe it into some, now if I did this right, this would be fine. Let's just do this. You can pipe it into a table type, like a data frame. But let's go ahead and let's pipe this now into a D table. So here we've constructed a D table directly from a CSV file. This will be pretty efficient to read in because we're using the tables.jl interface. We read things in incrementally, and under the hood, the D table will start building up all of those partitions. Now in this case, we only have one partition. I believe we can actually specify manually how many partitions we want. And I'm just going to keep going through. Now we have our D table. Let's just fetch that just so we see what that looks like, just to confirm it's what we expect. Now in this case, it looks a little bit different. We're actually, because we didn't specify a data frame as the table type, we're ending up with a name tuple of vectors, which is just another compatible table type. So that's what you get if you're piping a CSV file into a D table. So just be aware of that. We could, of course, say, hey, what's the table type of DT2? And this says name tuple. So you can at least know, hey, this is why this is happening. And if we want to, we should be able to type this into a data frame to get it as a data frame. So not terribly surprising. Now, let's just confirm that what we read into a D table and what we read into a data frame are actually identical. And they are. Under the hood, they are the same thing. They hold the same data. So kind of what you'd expect, but a quick sanity check to be sure about that. So let's write our table out into another CSV. And this time, we're actually going directly from a D table to a CSV. Now, again, this will go incrementally. So partition by partition, we'll start writing those out to a CSV so you don't, end up materializing a whole big bunch of memory if it's distributed across your cluster. Instead, you'll pull it partition by partition and then write that into the CSV incrementally. So if you're working with really large data, this can be really helpful. There are cases, of course, where, memory is over allocated. Say you have a D table that's distributed in your cluster, and if you were to combine it all onto one worker, you just run out of memory, and you'd get an out of memory error. Julia would be killed, especially if you're on Linux, that'll happen. If you run into any cases like that, where you're working with CSV data or distributed partitions, please file an issue and let me know. It's still a very new API, but we can definitely resolve those issues. It's not super easy to get out of core right, so always looking to kind of improve that support. So now let's just confirm again exactly what we expect. The D table that we wrote out into test2.csv is the same thing if you round trip through a data frame. So quick sanity check. Now, there's a convenient API. If you've used filetrees.jl, you might be familiar with doing this. They have their own way of doing this. But you can actually load multiple CSVs at a time into a D table. And it's pretty convenient. So the way it works is you call the D table constructor first with a so-called loader function, in this case, csv.file. And this is just the function that will be called once per file that's being specified, which is the second argument, test.csv, test2, test3.csv, etc. So if we call this, we can build up a D table from multiple files, especially if you have a lot of individual but large CSVs on disk. This can be very helpful for getting a lot of stuff loaded. And we can confirm the obvious, that this is the same as just concatenating our data frame 3 times. So in order, exactly what you'd expect. Now, you'll see that we have reported here by the D table that the table type is unknown. So when you're loading things in with this multiple files function, the D table doesn't actually know under the hood what kind of table type is being used. But similar to the table type function, which tells you what the underlying table type is, in this case, it says it's a name tuple, you can actually add a bang there, and it will update the D table's internal understanding of what the underlying table is. And so that it actually keeps that in mind, and it will use that for later operations to do some optimizations. There's not a whole lot of optimizations right now, but it is used in the code base internally just to make sure that we can eliminate some dynamic dispatch and we go directly between the table types that we're trying to use. So that kind of helps with efficiency. It's something that will probably evolve over time to play more of a role in the D tables API. So let's go ahead.
Julian, you need to reshare.
Yep. Switching back on.
Paolo shared.
I can kind of see this happening in the corner of my screen, so I don't know this is when it's starting. Cool.
Short question.
Yeah.
Why do we need to do this table.dash by hand and not just do it automatically?
I'm sorry, could you restate that?
So, I mean, for me, it seems as that the table type function knows exactly what's the table type.
Right. So
why do I need to do this manually?
So let's reload this real quick. And if we just do table type of DT3, the way table type and table type bang work, they both do the resolution internally to ask what is the table type underlying this dtable. So if you do this, it returns name tuple, but if you then ask DT3 again, hey, what table type do you have? It still is unknown, so it doesn't store it right now. There's actually, we should be able to see it. If we just look at the internal field, it's nothing. There's no table type stored internally. So you can query what the underlying table type is, but it's not necessarily cached. And I would imagine in the future, we might want to make that table type, the functional table type call, not actually resolve that. We may want to instead just return nothing if it's unknown. So if that ends up being something that you run into where the resolution of table type is really expensive and you'd rather just know, hey, this is unknown, the dtable doesn't know what it has, please file an issue and we can take a look at that. This API is still very much in flux. It's very new. So some of the decisions, we have the opportunity to change how we do things. So now.
Further question from the chat. This one, does execution of any operation is by default lazy?
Most of the operations that you use for manipulating the dtable are lazy. Table type is not. It's immediate, eager, whatever you want to call it. However, slight qualification to those statements is that Dagger has an API which I call lazy, which I describe as lazy. And that's truly lazy in that if you do not call collect or fetch, it is never executed. It will just sit there doing nothing. This API that we use for the dtable is called the eager API. It's still really lazy in that, in the sense that it's asynchronous. Once you say map or reduce on a dtable, it will start happening in the background, but you won't have to wait for that call to map or reduce to return before the result is complete. You can go on to fire a bunch of operations all at once, and they'll all be executing in the background, and then you can just wait on them and get the result with fetch, but they're still going to be executing. The next section on arrays that I'm going to show you still uses the old lazy API, and you'll kind of see this in practice. This will change. We are moving wholesale to the eager API because there's not often a reason that you want to just fire off an operation but not have it start executing. That's usually just kind of a waste of time if you're building a large graph of operations. But that is what originally Dagger was built on, as a truly lazy API. So we'll see that in just a second. Hopefully that answers your question.
There would be a second question. I think there was a really great answer to it. The second question is, does it assume the same structure across partitions? So does Dagger assume some uniformity?
That's a good question. So we definitely assume that the column names and types and orders of those are the same. However, I don't believe we have a restriction on the table type of the underlying partition. So you could have one partition be a data frame, then another be a type table, then another be an index table. I don't believe we have tests for this, but if you do want to try that out and it doesn't work, I think that's something that we're willing to support, because you can imagine constructing a D table from, maybe not with the APIs that are available today, but with a future API, you might want to pull in partitions from different sources. So maybe you have a CSV here, you have a data frame here, you have a database connection here, and you want to combine all of those into one table. That is something that we want to support. We may need to discuss how to support that internally in Dagger and what the API would look like for that. But that's definitely something that I want to have supported first class in some way. So if you're in that situation where you have multiple partition types and you're trying to combine it into a D table and either that doesn't work or operations don't work, please file an issue. We can take a look into that and see what we can do. And if there's no other questions, I'm going to keep going. Cool. So let's now look at the array API. Now, caveat, as you can probably see on my screen, the API is subject to change soon. I plan to switch this over to an eager API, like we saw with the D table, probably before the end of the year. And that will basically make it so that this API composes better with the rest of the array ecosystem in Julia and with base arrays. Currently, it composes in some cases, and in other cases, it does not, because certain APIs, they aren't happy that you're returning. Here, I'll actually show you. They're not happy that this rand call returns this allocate array thing, which doesn't support array operations. So this is something that will change. You will get in the future, the result of this next thing, which actually forces the computation to occur, you'll get what's called a D array. And this is actually going to end up being a real object that you can use directly just from this first call here. So I'll finish with my caveats, but just, be aware of that if you start using the D array today. So anyway, let's get back to the meat of this. So here with this rand call, what we're doing is it's similar to just a rand of 256, 256. You get a 256 by 256 matrix of float 64s. However, we have this blocks argument in the first position. What this does is it basically says allocate a random matrix of the given size in partitions that are 64 by 64. And so similar to how the D table has its own underlying partitions that are laid out in a sense linearly, you can kind of think of it like that. The D array allows you to lay out matrices or tensors of really any dimension as partitions that are basically laid out in, I think you would say, a Cartesian manner, where you can have blocks to quote unquote the right or below you or above you, etc. So this is useful for a lot of operations, which we'll see later on. It makes it possible to do a lot of local operations very efficiently and concurrently and with parallelism across a cluster. So that's what that is. Now, this allocate array object that we have here is lazy. So it does not do anything when you call this rand function. If in order to actually get a value out of it to actually compute the random matrix, you need to call compute. And that returns something called the D array, which is just a Dagger array. It is a distributed array if you're running in distributed mode. Right now, we're just using multi-threading because distributed has some issues. I don't think I actually pointed this out at the beginning. Distributed.jl that we're all familiar with has a variety of issues around multi-threading because it's such an old standard library and it's very complicated. So if you're using Dagger and you start mixing distributed computation with multi-threading computation, which Dagger will do automatically for you in the background, you may run into bugs. You may get some warnings like concurrency violations and things like that, depending on which version of Julia you are using. Excuse me. These things are being worked on. One of my collaborators, Christian, who actually built the D table API, he is working on fixing a lot of these bugs upstream in Julia's distributed. So As the months go on, you should see that it becomes more and more robust on Julia Master and newer releases. So just wanted to point that out. Back to the array demonstration. If you actually want to convert a D array to an array, you can simply call collect. Collect is compute and a fetching of the value. So you can call compute if you want to just do the computation but get back in a D array, or you can call collect if you want to go straight to the array representation of that. So that's how you do that. Now, this the array API supports a few different base APIs that you might expect. You can map across the values of the D array. As you'd expect, we increment by 3. You can do a reduction, and we can just compare, we won't look at the actual result of that, but it's the same, this reduce with a plus on the D array, dx, produces the same result as simply summing the underlying arrays of the D array. You'll notice kind of this weird indexing notation here that you wouldn't expect you'd need to do. I'm not really sure why this occurs, but there's some quirks to the API that'll be worked out in time. Now we can also do a mapmul. Now this is something that I've spent a lot of time using and working on as part of benchmarks. But there is a built-in mapmul operation in Dagger's D-Array, which is as optimized as it can be to work across a distributed system or multi-threaded system. So it actually breaks down based on the partitions. It will do a more efficient matrix multiply than you would do naively. And it allows a level of parallelism that, if done naively, you wouldn't get from a mapmul. So, mapmuls are very common operations. People like to do them at large scale, so we cater to that. So doing dx times dx and collecting that result is the same as just getting the underlying array of dx and doing the mapmul in a serial situation. It deserves reiterating that this operation here is executed with Dagger, multi-threaded and distributed. The operation to the right is not. I mean, there's some level of multi-threading parallelism built into Julia, but you are limited by what Julia gives you, which with the default build of Julia only gives you 8 threads. Dagger lets you go to whatever number of threads you have, whatever number of processes you have. It doesn't matter how big your distributed cluster is, or even if you're using a distributed cluster at all, this will work no matter what. There is also, I'm not going to show it today, but there is limited support for using GPUs to do operations like a matrix multiply. So hopefully in a future talk or presentation that I give, or some future blog posts, I'll actually go into depth about how to do that with GPUs, so that you can really, get the most out of like a supercomputing cluster, or if you have, a cluster at your organization or at home that has GPUs. But again, I won't detail that today. It's a little bit complicated to get working on, and it's a work in progress. So we can also do basic get index operations on a D array. So, we can select column or rows 2 to 3, and then all of the columns. And that is the same as simply turning this into an array and doing the same indexing. Now let's just take a look at this just so we know what that looks like. It's what you'd expect. So now there's also support for broadcasting. Broadcasting is something that, you always need it. It works great. I've put together some rather complicated broadcasting expressions with the D array, works just fine. And given that broadcasting builds up a big graph of expressions, we do the same thing. So Dagger is able to break down and basically construct a graph of operations pertaining to the broadcast expression you've given and optimize the execution based on that. So get more efficient, more available parallelism, better use the resources that you have. So These are all kind of simple. They work like you expect. And also, you can mix D-array with regular array operations, or potentially other arrays. Because, of course, dx is a D-array here, but collective dx is just a regular array. We fetched it to a standard matrix. So a lot of that stuff works. Some stuff does not. If you run into issues with this, probably just hold on for about 2 months, and we'll get this moved into a more composable API. But you're certainly welcome to file issues, and we can take a look at them in the meantime. So let's now go down into raw operations. Raw operations with the Eager API, which is the newer, more performance API that I've been focusing on. So this API is probably quite familiar to a lot of you here. It's used via Dagger.@spawn or Dagger.spawn. You can use the macro or not. And it works basically the same way as threads.@spawn. It, you pass an expression, usually a function call or something like that, and Dagger will wrap that in its own internal kind of task, which here is called an eager thunk. The name doesn't really matter too much, but it's a unit of execution that's occurring in the background, just like with threads.@spawn. And, similar to the rest of, to like the T table and the rest of Dagger's API, you call fetch to wait on the operation to finish and then fetch its result. Conveniently, and I think this is unlike threads.@spawn, at least in common usage, you can chain operations together with Dagger.@spawn, where A in this case is an eager thunk. It's a Dagger object lazily executing in the background. You can combine those with standard values like the number 3, and you can compose big chains with Dagger.@spawn and not worry about when they're executing or where they're executing. You can just write your code as quickly as you can, put it in a library, have very clean code, and then when you're done at the end, just fetch the final result. And in this case, it's 2 times 3 is 6, plus 4 is 10. So it's what you'd expect. This is convenient if you're just kind of prototyping code, or if you're writing a library that does operations under the hood of a greater API. And these calls compose with other @spawn calls. So if you're a library author and your library just returns one of these objects, you can pass it into another library that uses Dagger that passes these into @spawn or other places, and it will just work. They will all compose together. The underlying scheduler is the same, and it will treat them the same, and everything generally just works. Now, of course, unlike in real life where everything, or unlike in theoretical space, whatever you want to call it, where everything works perfectly and you write everything right the first time, we as humans make mistakes. We do things like trying to add the number 1 in the string A, and maybe by accident or trying out an API, and we get an error. And Dagger supports errors perfectly fine. What you'll get is if you create an error within an @spawn call, you'll get what's called a thunk failed exception when you try to actually fetch the results. And that will tell you some details like what were the operations that you did. So you tried to add the number 1 and the string A, and you get your standard method error as you'd expect. You get a stack trace, which may not be useful to you, but if you're reporting an issue, is useful to me to kind of debug these things. Now, of course, you can also have propagation of errors. So say we actually then try to use A, which we know through an error, to compute B. Now, if we try to fetch on B, we'll still get a thunk failed exception. What we'll also get is we'll see that it tells us the failure is due to a failure in another task with thunk. And that was our original A call to Dagger.@spawn. So you kind of get this chain of information saying, hey, B was not the source of this. A was actually the source of this. That's where the error came from, but it propagated down to B. So you don't get kind of weird results if something earlier on in your program threw an error due to a typo or some other reason, and then lower down it was indirectly used. You'll get a proper chain of custody, a chain of errors propagating. Now, if, for example, you don't care whether B threw an error or not, you don't even care about the result of B. You just want to wait for B to finish and know when B is done computing. You can use wait. I'm adding a semicolon just because it has a lot of output you don't have to worry about. But wait is great if you're kind of monitoring Dagger to see when certain things finish, if you're waiting on a certain API, certain operation to finish, but you don't care about getting the result, or if the result is really big and you don't really need it. So for example, we can actually just time this and just confirm, that's compilation time, but if we do it again, we see 3 seconds, it returns. So it works the way you might expect. Now, I know we're running a little close on time, so I'm just going to finish. There's 2 very small sections I'll go to. We're not going to see everything from them because they're a little bit finicky right now, especially with distributed being in the state that it's in. But we can actually exert some control over the scheduler. So this whole time, all of this code above that I have been showing you works agnostic of whether you are using multiple threads, you're using multiple processes. It doesn't care about that. It works all the same, and the scheduler figures out all of the details about where your tasks should go, how many should run at the same time, what resources to use. Sometimes, though, you do not want that. Sometimes you need to tell the scheduler, hey, this is what I want you to do. I want you to specifically run a piece of code here in a certain way. And we have a variety of like little knobs and switches that you can set to tell the scheduler, hey, constrain yourself to this set of processors or ways of computing. So the simplest one is called single. Now these options are just passed directly after at spawn and before the actual expression that you want to evaluate. In this case, we'll do a myID call. And basically what single says is specify the processor ID from distributed. If you call myID, you get 1 because we're on process 1. And single basically says only execute this code on that process. Don't execute it anywhere else. So in this case, of course it works. We've been using process 1 the whole time. If we had a distributed cluster set up with other processes, you could pass 2, for example, or 3, or whatever the number is, and it would only execute there. Now we can get more fine-grained in this. So in this session, I should have a few threads. I believe I have 4. Yep. And so we can actually specify what thread we want to use. Because under the hood, Dagger executes units of work when executing in a CPU execution style. We execute code on a specific thread. We specifically say this piece of work will start working on this thread. We don't just throw it to threads.atSpawn and let it put it wherever. We take pretty careful control over where code executes. And that helps the scheduler be optimal in various cases where there's a lot of work going on. So let's construct something called the thread proc. This is just an underlying representation of the thread that is on worker 1, process 1, and thread 1. And we can specify to Dagger that we want to exactly execute only on that thread on that processor. And what we're going to do is we're going to ask for the thread ID. And basically while that's executing. And the thread that was executed on was thread 1. Now let's actually execute on a different thread. So let's specify what thread 2 looks like on this process and execute from there. So we see that we specified only execute on thread 2, and the thread ID while we were executing was thread 2. So that's what you'd expect. Now I've only got 4 threads in this session, but let's forget that for a second and think that, oh, maybe we allocated 8 threads, and so maybe we have thread 7. Well, no, if you try to do that, Dagger will say, hey, scheduling exception, you can't do that. You can't try to execute on a thread that doesn't exist. So that's pretty straightforward. Kind of tries to isolate you from making little errors and accidents, and will throw an error that kind of informs you, hey, you did something wrong. You specified a constraint that we can't satisfy. So that's basically it. I'm not going to go into some other details. Setting up some of this other stuff that I wanted to show is a little bit finicky. So hopefully in the future, when you check out Dagger, you'll be able to find these things. They're in the documentation, and you can give the more fancy features a try. But yeah, that's it. That's all I've got for this presentation. Thank you for listening. I'd appreciate any questions that you guys have. I'd be happy to answer them.
Thank you very much, Julian.
Of course.
Yeah, quite a pleasure. We have time. We also have still a lot of participants being here. Thank you for staying with us. So please share all your questions you have. I can start with one question. There's the big question whether in distributed computation I've been using Spark quite some time, and the most important operation actually is the joining of distributed tables.
Right.
Does Dagger support this or plans to support joining D tables?
Absolutely. So joins is something being worked on by Christian, my collaborator, who is the maintainer of the D table. And as you may know, if you've seen benchmarks of Spark and other distributed or multi-threaded table libraries, joins are very hard to get right and to do them efficiently. So he's spending a lot of time getting an implementation together which works efficiently and doesn't take an absurd amount of memory for what is really a small set of tables you're joining. Because with joins, you can very easily end up in a situation where you allocate a ton of memory just to come down into a final table, which is actually not that large. So he's working on that. There is a PR open. If you check Dagger's pull requests, there's a PR open for left join. I'm looking forward to getting that merged probably within the next month or so. Depends on how much progress he makes on that. But it's definitely an API we plan to have, and it's going to be a key area of optimization for Dagger that we're probably going to have to sink a lot of work into to make sure that that works really well. So bottom line, yes, it will happen soon.
Nice. Thanks a lot. We have 2 questions. The first one being also a bit long. So big thank you. Wondering what is Dagger's built-in heterogeneous scheduler that can dispatch units of work to CPUs, GPUs, and other accelerators? Is it Julia or something different?
So Dagger has a single scheduler. You can't really pronounce it, but it's just SCH. The built-in scheduler is flexible. It has the ability to detect and dispatch work to different kinds of accelerators other than CPUs. The Dagger.jl repository does not directly include logic for this, however, for anything other than CPUs. Because of course you don't want Dagger to depend on the GPU libraries, you don't want to include that level of complexity and the necessarily expensive pre-compilation required to have them as a dependency. So what we have is a library called Dagger.jl. And that library is essentially plugs into Dagger scheduler and exposes GPU resources to the Dagger scheduler so that Dagger scheduler will see, okay, I have this number of threads. I also have these attached GPUs. Currently supporting NVIDIA CUDA and AMD GPU ROCm, and they're not enabled by default. So if you were to load Dagger GPU and then do computations, you will not use GPUs. Your operations will not use GPUs automatically. And that's because a lot of code doesn't work on GPUs. We don't want to just see that Dagger GPU is loaded and then just throw work at GPUs and then have it throw an error because those operations aren't supported on GPUs. Instead, you can specify to Dagger that a given operation or set of operations may use GPUs if the scheduler deems it, you know, a good idea, basically. Or you can force it to use a GPU. There's also a way to do that. All of this is kind of detailed in Dagger's documentation. There are some parts of the docs that are a little bit lengthy on this, but I believe if you look at the processors part of the documentation, that should detail how to use Dagger GPU. You can also take a look at Dagger.jl and look at the tests, and those have some examples of how to use it and how to force using GPU execution. I will say that it is, again, another area that is work in progress. It's hard to get right, and it's hard to make it flexible enough so that it does what you'd expect. So it's coming along, but it's going to take a little bit of time. I'm still working on getting transfers between GPUs on the same machine to be efficient. I have an open PR for that, and I'm hoping to probably get that merged in the next week or so. And if you use a library like Daggerflux.jl, which you may have heard of recently, which is Dagger integrations with Flux, you'll actually be able to automatically use GPUs for Flux models. And we're hoping we can get extremely competitive performance with GPUs that rival like PyTorch and similar libraries in the Python ecosystem. So definitely look forward to that in the next week or two.
Awesome stuff. There's a second part to this question block, and this asks to compare Dagger, distributed, and especially GASP, or GASP, don't know how to pronounce it, a Julia wrapper for global address space toolbox, MPI 3 one-sided remote memory access things. Yeah, could you compare them?
Yeah, this is basically, I group all of that into MPI style computation. Dagger is not currently targeted at the kinds of computations that MPI is very good for. GASP is one way of accessing that, is my understanding. Dagger is more focused right now on dynamic units of work, where you may have a very irregular computation graph. You may not have like a very static grid where you're doing operations almost in lockstep on elements of that grid. We do plan to optimize this area in probably over the coming year. And given that I work at the Julia lab on HPC problems and I work with GPUs pretty frequently, this is an area that we're looking into heavily. But MPI is MPI has had a very long history and a reasonably successful history because of how static and regular programs tend to be when they're written with MPI. It's kind of hard when you have a dynamic scheduler to then get into the static scheduling space and be efficient. So it's probably going to take a little while. But we definitely plan to be able to do some of the same things that you might write in MPI with Dagger efficiently, using GPUs, using fancy network fabrics like InfiniBand and stuff like that. We definitely plan support for that. It may just take a little while, but we do have some prototypes that we've built that have worked for certain problems. So it's coming in the near future or midterm future. But it may be a little while.
Nice.
I'm going to just go ahead and see the rest.
One further question. I hope the last answer answered the question, but I think it was pretty detailed. There's a completely different one, and that's about which functionality Dagger actually supports. So what sort of constraint are there on the functions that Dagger can execute? So you showed the example of my ID, thread ID, and yeah.
That's a great question. So that's something I actually use. I usually like to start presentations with is specifying the constraints on Dagger tasks, but sometimes that distracts from being able to use the API. So Dagger's API is focused on functional programming. And not just functional, but kind of almost pure functions. So if you pass a function to Dagger, and you can pass any function to Dagger that you want, but if you pass a function to Dagger which is not functional, in other words, it may have side effects, it may do things that, it may mutate its inputs, or it may spawn a task that later mutates its outputs or something like that, I generally will consider that function to have undefined behavior in Dagger, because we don't want to restrain Dagger's scheduler under the assumption that every function might be mutating the input arguments or is generating side effects. We don't want to have to do that. So if you show me a program, if you file an issue and you're like, this isn't working, and you're doing mutating operations or you're generating side effects, and there is the possibility for that to not work, depending on where and when Dagger schedules your work, that is undefined behavior. However, that said, in the future, I do plan to add support for mutable data, mutable arguments, essentially, where a piece of data is locked to a given location. We don't attempt to serialize it anywhere. We don't attempt to move data around, and we basically teach the scheduler, hey, this piece of data, this argument to this function is mutable. It will change. Do not try to cache it. Don't try to make copies of it or anything like that. And that'll be useful if you're doing things like, say you wanted to, implement a histogram with, multiple threads and multiple processes, but, you wanted to use just a single data container for that histogram. In the future, you will be able to do that. You'll basically be able to mark that piece of data as mutable, and then Dagger's scheduler will force everything that operates on that histogram to operate in what's called the same scope, in the same, usually on the same process, using the threads in that process or on a given GPU, so that it can directly access that data without any copies, without any data movement, so that you can do, say, a reduction directly into a container and reuse memory. Side effects probably may or may not be supported as defined behavior, depending on what it is. Reading CSVs, for example, works fine as long as you can read it from any node, or if you do the reading outside of Dagger. But if you say, I actually had this when I was putting together another presentation where I had some input files that were only on one of the servers I was using, but the other server didn't have them. And then I tried in Dagger to read that file. It sometimes worked and it sometimes threw an error. And that's because, of course, that other server didn't have those files, didn't know where to go to actually get those files. So sometimes you'll get an error from trying to do this. Sometimes it'll work. Just try to keep in mind functional programming. If you're using Dagger.spawn, they should be functional programs. If you need to do something that mutates or has side effects, for now, do it outside of Dagger. In the future, we definitely will have mutability support, though. That is something that is very, that's on my short-term list of to-dos. So that's a great question.
Thank you very much.
Of course.
There just popped up another question.
As for Daggerflux, Alpha Zero. Okay. Yeah, this is a great question. So I would have to ask Daria about this, who is the developer of Daggerflux. I think that, let me just think about this for a second. It should potentially just work, because I believe we wrap, with Daggerflux, when we wrap, say, a flux.chain object, we wrap it with kind of our own chain object. but it works the same. Like you can call it as a function, and you should be able to query the layers. We'll probably have to look into this. AlphaZero is Jonathan, who develops that, is actually, we're pretty often in contact with him at the lab. So it's definitely something that is on our radar for probably the midterm timeframe, I'd imagine. I'm not sure it works right now, though. That's basically the bottom line answer. I'm not sure it works, but you should definitely give it a try if that is something that you want to give a go. And if it doesn't work, definitely file issues, and we can look into getting that to work. And then your second part of your question is Dagger something like a next stage of Julia parallelism that is going to supersede distributed? That is my hope. So I believe that distributed.jl is the wrong mode of programming for most users. Threads.atspawn, for example, is a great mode of programming. It has a few issues, but it is generally a superior API if you're doing multi-threading. But we don't really, without Dagger, we don't have a way to do something like that, to have composable distributed programming. And that's what I want Dagger to be. I want Dagger to be the library that lets you compose distributed programs and multi-threaded programs and heterogeneous programs that use GPUs and other accelerators like that. That is my goal for Dagger. I've been working over the last 2 years to make that a reality. The processor support and GPU support, as well as the Eager API, are both targeted at this goal. They were created specifically with the intent to solve the problems that distributed does not solve efficiently or in a productive manner. So yes, Dagger, I consider Dagger to be the next foundation for distributed and multi-threaded programming in Julia. I would appreciate any help making that become the case, because that's a large hill to climb. But I think Dagger is already well on the way to doing that.
Wow, impressive. A related question from my side. There is this package JuliaDB, which is out there for quite a while, but a little bit missing maintainers. Is Dagger actually a continuation of JuliaDB in a sense?
I would say yes. So JuliaDB, I've actually done some contributions to JuliaDB, and unfortunately the code base is just not, it was kind of written in for a specific kind of problem that Julia Computing was trying to solve, or for a specific set of customers, and it was, in its time, it was great for that. Unfortunately, that code is not really flexible or composable enough to move into this new age where basically everything in Julia composes amazingly well to some extreme. So it's my belief that Dagger's D-table, along with the upcoming support for storage and memory awareness in Dagger, which I'm actively working on, will supersede JuliaDB and allow us to have a way to do database-like operations that JuliaDB was originally suited for, but to make those composable and to use modern practices and modern APIs. We already saw the CSV reading and writing support today. That is one of the first parts, because JuliaDB is very focused on reading and writing to and from CSVs. We have that today. Really, the next big thing is storage awareness. So doing things like swapping memory to disk, or doing true out-of-core computations where your data stays on disk and only sometimes you read it in temporarily just to work on it, and then you throw away your in-memory copy and just leave it on disk. That is coming in probably the next month or two, depending on how well things go. And once that is available, I imagine that will have covered quite a lot of ground that JuliaDB already has. Joins are also a big part of that. And those are also coming in the near term. So I would definitely say yes, JuliaDB is essentially a predecessor to current features that Dagger has, and we will see JuliaDB Instead of being improved in maintainership, the maintainers becoming more active, likely Julia DB will kind of go further and further into the unmaintained state while Dagger picks up all of those features and more. That's a great question. That's something I've been asked quite a lot, actually.
Thank you. Yeah, it's impressive to hear. And I hope it's going to get there. Yeah, it's really yeah, a nice goal. I would have another question.
Sure.
Because these tables, they are so lovely supported with a unified API. There's the table.jl and there's the query.jl. And I want to ask, because in your examples, you have been using some base functions, but also like Dagger.groupby. Have you thought about supporting unified APIs, or maybe you're doing it already?
Yes. So I generally want to support as many either base standard lib or basically agreed upon ecosystem APIs as we can. The tables.jl support is evolving, but notably things like joins and other complicated operations, I don't believe we actually have a unified, we may have a unified way to specify them with table operations.jl, but there's not really fallbacks for operations that work everywhere. Especially with joins, because joins, if you implement your joins wrong, or you just use some generic implementation, you're going to have a very bad time with memory usage and performance. So I am a huge proponent of following existing APIs that we have and kind of working on getting everyone to use the same front API, and ideally have some generic fallbacks for operations that aren't yet implemented. I think that groupby may actually use may be table operations.groupby or something similar to that. But if you find that that's not the case, definitely file an issue, and we can take a look at that and see if we can get a little bit closer to kind of ecosystem acceptance. And composing with other parts of the ecosystem. That's a huge goal for us.
Cool. Yeah. I actually also had sometimes problems to find the unified interface for tables. Thanks also for your perspective that there indeed is maybe not yet the full-fledged API, but I guess it's going to come then somewhere.
Yeah, probably midterm future, next half year or so. My collaborator is working on his master's thesis, but after that, he's hoping to have time available to keep working on the D table, and he's been driving a lot of these changes. Christian has been a huge help. I mean, he is a co-maintainer, and he is the maintainer of the D table API, and I'm sure he'd be happy to kind of discuss and work on getting these APIs unified among the tables. So, yeah, great question.
There's one other question from Simon. Thank you, Simon. So there's the concrete question whether you plan to support Intel's GPU.
Yeah, I'd be happy to. If I do not have access to Intel GPUs myself, I may invest in some in the future, but we don't really have, because Intel hasn't, I would not take this at face value. This is my own beliefs of the current situation. I believe that Intel isn't providing us a lot of CI resources that we can easily access. And that kind of hampers one API uptake into the ecosystem. So it's kind of part of the reason that you're not seeing it everywhere. I personally, as I said, I don't have a system to test on, and at least for CUDA and AMD GPUs, I do have access to a lot of those, so it's kind of easy for me to test things and set up CI. I think we'll need to see where things go. Of course, if anyone wants to contribute a backend to Dagger GPU, I'd totally be happy to. We wouldn't require CI to be available in order to do that. I do want to see one API supported throughout the stack. So It's just not something that's on my radar right now until either grants come through to the lab for working on support, or if it becomes part of some other project, or someone is working with us to drive this. So yeah, not near future unless things change, but certainly contributions will be gladly accepted.
Okay, great. Yeah, then maybe one last question from me. I would be interested, have you tested how large Dagger can scale, up to which amounts of data or how many machines?
Yeah, that's a great question. Alan Edelman, the PI of the Julia lab, has been definitely pushing on me a lot to push Dagger as far as possible, really into the supercomputing realm. There's a few reasons why Dagger cannot scale to, say, supercomputer sizes, or even just like big data sizes. One of them being that the scheduler just runs on one thread on one process, something I plan to change. But when you start doing, basically the only way to scale to that size is to distribute your scheduling decisions across your cluster. But doing that is hard because things like distributed consensus are hard. And there are many situations where something that works in one setup does not work well in another setup. So to answer your question specifically, we have a set of machines that have 128 threads, and I regularly run Dagger on those. And depending on how many units of work you give to Dagger Scheduler and how expensive those units of work are, how long they take to compute, Dagger can either do really well and utilize all 128 threads, or we get stuck at like 8 threads. It's something that I plan to work on and plan to improve, but it's not easy. But it's coming in the near future to distribute the scheduler, and I imagine that if I do it well, we can end up with a situation where we can basically scale as far as distributed.jl will let us scale. That would be the other potential bottleneck. But yeah, that is on my radar, to scale to supercomputing sizes, because we have access to supercomputers and we want to be able to run Julia code on Dagger on supercomputers. So yeah, that's something on our radar.
That's very, very big.
Yeah. So.
Okay, so yeah, I think, so if there are some more questions, please, last chance for the day.
And if you have other questions, you're always welcome to file issues or ask me on Slack, on Discord, or Discourse, excuse me, on Zulip. Send me an email if you have my email address, whatever. I'm happy to answer questions and help out with whatever you're doing. So.
You also shared the little source code for the examples of today.
Yes.
We will put this into the meetup as a comment below, that you also can replicate what we've been doing today.
Cool. Yeah, you'll at the bottom of it, you'll actually see some code for setting up the web dashboard that I added to Dagger about 2 months ago. It has some issues that I found while putting together this presentation, which I plan to fix. You're, of course, welcome to file issues. It's in the Dagger.jl repository. It's just a subpackage. But if you run Dagger's benchmarks, which are built in, there's docs for how to use them. You can actually get the web dashboard running really easily. So definitely check that out if you want to kind of see what the scheduler is doing under the hood, all the different operations that it's doing. It has a lot of information. I wish I had a little bit more time to present it today, but unfortunately it's just a little bit finicky. So.
Okay, great. Then I want to thank you again, Julian, for being here today and giving us the introduction to Dagger and all the deep questions and deep dives. It was a pleasure to see this distributed computing really getting part of Julia's standards. And yeah, thanks you also for your work on it and pushing it further.
Yeah, thank you so much. Appreciate you setting all this up and organizing this and having me out.